So, hello everyone. Following the last lecture of metabolic energetics, now next it is important to understand and discuss this energy balance. So, in the last lecture what we discussed was the metabolism. We took few examples like carbon catabolisms, respiration and photosynthesis, and we calculated the energy efficiency, means how much energy is required and how much energy is conserved in the form of ATP or in the form of chemical compounds. Now, next we are going to discuss today is energy balance, because what it says that total energy is also conserved. So, if you remember the first law of thermodynamics, so it says energy can neither be created or neither destroyed, only the form of energy can be converted from one form to another. And in the bioprocess, what will be the different source of energy? So, one of them is the heat of reaction, that we will be discussing the heat of reaction, how to calculate it. So, as we know, the bioprocess or any biological system, they are not very energy intensive, and typically if you see fermenter or enzymatic bioreactors, they are operated at ambient temperature and ambient pressure, but still as there is a metabolic pathway, heats are released, and these heats, although its amount is not very high, but still can damage to the cell or denature the enzymes. So, what it says, we need to have this temperature control facilities to maintain the optimum process temperature. So, in order to provide this temperature control device, we need to do this energy balance. We have to see the energy flow in the system and how much energy is flowing out of the system. So, we apply the law of conservation of energy to determine the amount of either heating requirement or cooling requirement. For cooling, typically we use cooling water, for heating we use steam to maintain the optimum process temperature for a given bioprocess system. So, as I told, this biological system is an open system where the transfer of mass as well as the energy takes place. So, here you can say mass is coming in, mass is going out, work is being done and heat is being released. W is the work and Q is the heat. So, what is the source of energy? There are mainly three sources: heat of reaction, sensible heat exchange or change in the sensible heat, and heat of mixing, particularly if you are dealing with this agitator. So, we require the power requirement for the mixing that generate the heat. So, like mass balance, we can also do the energy balance. So, it says in how much amount of heat is coming in, let us say m, I, H is the enthalpy, H is enthalpy, in minus out, m O into H, minus how much heat is lost, Q, what is the work done, Ws, this equals to delta E. Delta E is the change in the energy or the similar to accumulation. Now, we know at steady, if you consider a steady state, the accumulation term will be 0, and further if you consider the adiabatic system, if there is no heat loss, in that case one can also put Q equals to 0. Now, how to calculate the heat of reaction, that is important here. So, for heat of reaction we can calculate based on the enthalpy. If enthalpy is known to us, the heat of reaction will be delta H reaction. This is enthalpy of product minus, you can write N here or M here, enthalpy of reactant. So, many times this enthalpy value may not be known to us. So, another option is to calculate in terms of heat of combustion. If heat of combustion is there, so in terms of heat of combustion it says delta H reaction equals N del heat of combustion here reactant minus N delta H heat of combustion product. So, this is for the reactant and this is for the product. So, based on the, if the heat of combustion is known, we should be able to calculate this heat of reaction using the concept of heat of combustion. Now, why we apply the heat of combustion? There is also advantage of applying this concept, because heat of combustion for, let us say, for carbon dioxide, for water, that is 0. It helps in doing the overall the energy balance. So, if we go back to the last, what it says is enthalpy inlet of enthalpy of outlet minus Q plus W equals 0 at steady state. So, this delta H product minus reactant. So, we can write this as minus delta H reaction. So, these two can be written minus delta H reaction. In addition, what happens sometime in the bioprocess, there is a phase change. So, in that case we have to use the term latent heat. So, it becomes minus AMV, amount which is participating in the vaporization or phase change, into delta HV, that is the latent heat. So, we are going to replace these first two term is this minus Q plus W. So, modified equation is minus delta H reaction minus latent heat term minus Q plus W equals to 0. So, MV is the mass of liquid evaporated and delta HV is the latent heat of vaporization, because many times in the bioprocess we may see there is a phase change, particularly when we are dealing with steam. So, what we can see here, in the case of metabolic reaction they generate 5 to 20 kilojoule of heat per second per meter cube of fermentation broth if the substrate is carbohydrate, and if you change the substrate as hydrocarbon, this energy increases to 60 kilojoule, up to 60 kilojoule per second. In anaerobic culture, when you sparge with dry air, there may be evaporation loss and it removes about 0.5 kilojoule per second as latent heat. Further, as I told, apart from the heat of reaction, there is other input like heat of mixing or the soft work. It varies between 0.5 to 5 kilojoule per second per meter cube, and if you see this value is much smaller than the amount for the heat of reaction. So, typically the sensible heat and the heat of mixing are several order of magnitude smaller than the heat of reaction. So, many times when we calculate the heating or cooling requirement, we can directly go using delta H heat of reaction. We can ignore sensible heat and heat of mixing part. Now, heat of reaction, there can be option where oxygen is working as the electron acceptor. So, as I told, heat of reaction you can calculate based using the heat of combustion. So, we need to find the heat of combustion, that says it is minus Q. Q is heat evolved per mole of available electron transferred to oxygen during combustion, into gamma is the degree of reduction of the compound. This is relative to nitrogen, not ammonia, and Xc is the number of carbon atoms in that molecular formula, and typical value of Q is known to us. It says 111 to 115 kilojoule per gram mole. So, one option is, if you are having this oxygen as electron acceptor, so what we know, for each molecule of oxygen consumed, there will be typically 4 electron transferred. So, it will be 115 into 4, that will be 460. So, it says 460 per mole of oxygen consumed. So, from the stoichiometry reaction, if you can find what is the amount of oxygen consumed, if you can find the moles of oxygen consumed, we can directly calculate the heat of reaction using this value. Now, there will be the second case where oxygen is not as the principal electron acceptor. So, in that case, what you have to do, this, let us say this is a carbon source, this is a nitrogen source, there is no oxygen here, this is biomass, carbon dioxide, water and your product. So, here what you have to apply, delta H reaction is delta H combustion of the substrate. What are the inlet? Is a carbon source and the nitrogen source. What is the in the out? Out's product size is the biomass and the your product. So, in this case we require the heat of combustion for biomass, we require the heat of combustion for nitrogen source, we require the heat of combustion for this biomass as a product, and heat of combustion of your given metabolite. So, these heat of combustion need to be known, and typically they are given, and once they are given, we should be able to calculate the heat of reaction when oxygen is not a principal electron acceptor. So, let us consider this reaction here where oxygen is a principal electron acceptor. So, what it says is biomass is oxidized, it is converted to carbon dioxide and water and N2. Here it says assume 5% S. What is the consideration of S? Means you have to take care of molecular weight. So, here the molecular weight of biomass will be, let us say if it is 24.6, if you consider 5% as, you have to divide by 0.95, and this will be actual molecular weight of biomass will be 25.9. And how we can calculate? Delta HC0 minus Q degree of reduction into Xc. The degree of reduction is 4.8, Q is, you can take 115, Q is 115 kilojoule per gram mole, and if you multiply this, you will be getting kilojoule per mole, and further it can be converted to kilojoule per gram as its molecular weight is known to us. So, we are getting the value of minus 21.3 kilojoule per gram, and this matches very much with this typical value of bacteria, that is 23.2 kilojoule per gram, and for the yeast this is 21.2 kilojoule per gram. So, these are the typical value. So, even if you know the what is the your biomass, it is bacteria or yeast, one should be able to directly use this typical value of heat of combustion. Now, here let us take one example. What it says is Saccharomyces cerevisiae is grown anaerobically. Anaerobically means oxygen is not the primary electron acceptor. Alright. Glucose is used as a carbon source, ammonia is used as a nitrogen source. What are the product? Glycerol and ethanol are produced, and at steady state net mass flow to and from the reactors are given here. So, glucose is coming in, ammonia is coming in, cells are out, glycerols are out, ethanol is out, carbon dioxide is out, and H2O is out. In addition, the heat of combustion is given to us for glucose, ammonia, glycerol and ethanol. As we know, this heat of combustion is 0 for carbon dioxide and water and nitrogen gas. So, here the heat of combustion is given in terms of kilojoule per mole, then same can also be converted to in terms of kilojoule per kg by dividing again with this molecular weight of given compound glucose, ammonia, glycerol and ethanol. So, first let us draw this flow diagram. This is a bioreactor. Glucose, how much glucose is coming? 36 kg per hour. How much ammonia is coming? These are the inlet stream 0.4 kg per hour. What is outlet stream? 2.81 kg cells, 7.94 kg glycerol, 11.9 kg per hour ethanol and 0.15 kg per hour of H2O along with carbon dioxide. These are going out, these are outlet streams. Now, what we have to calculate here is estimate the cooling requirement. It means how much energy is released to the environment. So, what we have to do for this question? You have to do the apply the energy balance. So, it says what are your inlet? Inlet is your glucose plus ammonia degenerating our biomass plus glycerol plus ethanol plus CO2 and H2O. What we have to calculate? We have to calculate the Q. So, if you remember what is the energy balance equation, it says minus delta H reaction minus mv delta HV taking care of latent heat minus Q plus W equals 0. So, as there is no work done, the W is also 0. There is no evaporation loss mentioned here, so this term is also 0. So, it becomes Q equals minus delta H reaction. So, what you have to calculate here is the delta H of reaction, and as oxygen is not the primary electron acceptor here, how we are going to calculate delta H reaction is in terms of heat of combustion of reactant minus heat of combustion of product. So, what are the reactants here? So, it says M delta Hc of glucose plus m delta Hc of ammonia minus m delta Hc of outlet is your biomass minus m delta Hc of glycerol is one product minus m delta Hc, another product is ethanol. And this delta Sc for CO2 and H2O is 0. Now, it is easy now because mass flow rate is already given to us, we need not do this material balance. Otherwise, we need to first do the material balance to get this mass of each stream coming in and going out. Once it is known, heat of combustion is already given, that was given in terms of kilojoule per mole, that can be converted to kilojoule per kg because mass flow rate is given in terms of kg. So, we can divide with respective molecular weight, and once we apply here mass into heat of combustion of glucose, mass of, what is the mass of glucose? 36. Similarly, mass of ammonia 0.4 kg into heat of combustion of ammonia minus biomass 2.81 into heat of combustion of cells, then glycerol minus 7.94 into heat of combustion of glycerol, and ethanol 11.9 kg. So, if you apply this, we will end up with delta H reaction equals minus 1.392 into 10 to the power 4 kilojoule. So, as we know, this Q will be minus delta H reaction. So, Q will be again 1.392 into 10 to the power 4 kilojoule. So, positive value means this amount of heat to be removed from the system. So, here what we trick here is you have to calculate the heat of reaction, and if it is this anaerobic process, you have to calculate based on the heat of combustion of reactant as well as product. Now, one second example we are going to take here is citric acid production. For a period of 2 days, 2500 kg glucose and 860 kg oxygens are consumed to produce 1500 kg of citric acid, 500 kg biomass and other product. What is the nitrogen source here? Ammonia is the nitrogen source. So, here it says oxygen is consumed. Oxygen is consumed means oxygen is working as an electron acceptor. So, we should be able to easily calculate the heat of reaction using the first concept. Power input to the system by mechanical agitation to the broth is 15 kilowatt. So, there is a supply from this heat of mixing, and in addition there is a loss of water also, 100 kg of water is evaporated also, and now we have to estimate the cooling requirement. So, latent heat change for water at 30 degrees is already given to here 2430.7 kilojoule per kg. So, what you have to do, first draw the flow diagram what is the in is glucose is coming in, ammonia and oxygen is coming in. What is outlet is citric acid, biomass and water vapor. Heat is being released. In addition, there is a supply of heat of mixing, that is 15 kilowatt. So, 15 kilowatts equals to 15 joule per second, right. So, this will be 15 kilowatt equals to 15 joule per second. Now, again we have to do this energy balance here. So, how we are going to do this energy balance? We are having here glucose, oxygen, ammonia, nitrogen source. This is generating to biomass, plus citric acid, CO2 and H2O. So, we did not do the material balance as because all the masses are given to us. Now, we can directly go for energy balance. The energy balance equation is minus delta H reaction minus mv delta H V minus Q plus W is 0. You have to find the value of Q. Now, it is interesting because this is aerobic process, we can directly calculate the delta H of reaction. Delta H reaction will be what is the amount of oxygen consumed? 860 kilojoule. So, it becomes, if you remember the last discussion, for aerobic process you can calculate minus 460 kilojoule per mole of oxygen consumed. So, this will be directly equals to minus 460, how much oxygen is consumed? 860 gram, you can convert in kg, you can convert into gram divided by its molecular weight 32. So, heat of reaction is directly coming as minus 1.24 into 10 to the power 7 kilojoule. Now, mv, how much water lost is 100 kg, it is already given. Latent heat of vaporization is also given to us, in W. What is the value of W? W is 15 kilowatt, means 15 kilojoule per second, and this we are continuing for 2 days. 2 days means 24 hour into 60 into 60 into 2. This is 2 days, I converted into second, 15 kilojoule per second. So, now it will be 2.59 into 10 to the power 6 kilojoule. So, W is now also known to us, this is also known. So, we can directly calculate the value of Q here. Q will be now minus delta H reaction minus mv delta Hv plus W, and we have already calculated all the parameters. This will end up with Q as 1.47 into 10 to the power 7 kilojoule. So, again the value of Q is positive, it means this much amount of heat will be released and that need to be removed from the system. So, it requires the cooling arrangements. So, in this way we should be able to apply both material balance and energy balance for any given bioprocess problem to analyze what is the mass requirement as well as what is the heating and cooling requirement. So, I will stop here. Thank you so much.